The focus of the talk will be the control of the organism, specifically coccolithophores, on the formation of unique crystals. And I will start with telling you what do I mean by biological crystallization. We are focusing on the process of the formation of the mineral. So from the one side, we have the material science aspects of the formation because these are crystals. But from the other hand, we have the cell biology because this is happening inside of the cell. And the way that we like to look at it is to call it material science in vivo. And I'm starting with showing you an image of the group about a year ago. So these are the people that are doing the work with me. And I will start with some kind of general motivation. I know it's not really important for this group, but I like to give this example because what we see here is the skeleton of a marine protist and a cantharian that is quite common in the sea. And it looks like this is the model thing that you want to study if you are interested in biomineralization, because it has these amazing shapes that are both aesthetic, but are also species specific. They are under the genetic control. The structure of the mineral is very preserved. Every one of these elements is a single structure. And here, even the composition is amazing because evolution shows that this protist will form the skeleton from strontium sulfate. Strontium is a very minor component of seawater, and still this is what they do, and this is evolutionary concern. But then when someone really wants to work about it, we need to take into account that these creatures are still not culturable for more than few weeks or so in the lab, so it's very difficult to grow them. We don't know enough about the genetics. And if we want just to focus on the mineral and to characterize it, it's very difficult because strontium sulfate is very soluble. If we just take it, it's very easy to dissolve it, and then we have nothing to work with. So it's like the good and the bad of wanting to study biomineralization processes. Not everything that looks nice and interesting we can really do. And because we are interested in a controlled mechanism of biomineralization, I will just highlight what do I mean by this notion of controlled crystallization, because if we are looking on a spectrum, on the one hand, we can have a non-controlled crystallization. This is the slide that you can see in an optical microscope from some limestone. And there are crystals. The crystals are not oriented, they don't have the same shape or morphology. Actually, the only thing that seems to have a shape are fossils. So they are biologically relevant. So this is something that is randomly happening when chemistry is ruling. Now, organisms can control crystallization to several degrees. One example is this calcite crystals of the chicken egg, which are basically just crystals that are starting to grow from an organic membrane outward. So there is a preferred orientation, but it's not very controlled, and there is nothing much more than that. When we look at other examples, we can see some other organisms that control to much a better extent. Here is an example from an echinoderm skeleton that is creating every one of the elements from a single crystal of calcite. So this unique morphology will actually diffract X-ray as if it was just a single crystal. And the way that these organisms are controlling the morphology, the orientation, is under the biological control. And maybe the most interesting control behavior is when you can find one architectural element. This is the coccolith or the coccolithophore that is made of several crystals, but each one of them has a preferred orientation, a preferred shape, a preferred location when it is controlled. So everything here is under the biological genetic control of the cell. And for this, among other reasons, is why we are focusing on organisms that can have this degree of control on their crystal formation, because from this we can study what are the tricks of biology. And in my group here in the Weizmann, what we are doing is we are studying two different types of unicellular algae. One are the coccolithophores that are producing this calcium carbonate, calcite scale, which One of these scales we call the Coccolith, and they are covering the cells. And the other group are diatoms. They are also making beautiful mineralized array, but they are creating their cell wall out of silica. Today I will focus only on the coccolithophores, even though there are very similar questions and things that we want to learn that we benefit from comparing the silica case to the calcium carbonate case. And I will give just one highlight slide about coccolithophores because they are very important, not only for the beauty of their coccolith, and this is because they have a very important environmental impact on the global system. They are part of the phytoplankton, so the photosynthetic marine eukaryotes. Altogether, they account for about 1/3 of the global photosynthesis. The coccolithophores themselves are thought to be about 10 to 20% of global photosynthesis. Because they also calcify, they also contribute to the sequestration of carbon to the deep sea because the coccolith are sinking down. And here they are even more important because they are, together with the foraminifera, of the two dominant groups. And as organisms, they are also the source for many ecosystems and the food chain in the ocean. And what we know is that over geological timescale, the coccoliths that sedimented to the bottom of the ocean also can give rise to chalk formations like this beautiful white cliff. So this is all interesting on a global scale, but if we want to understand the process itself of mineralization, we need to change our focus from this big ball to a much smaller ball, which is the single cell. And in this beautiful movie, you can see it's accelerated, but this is the process of coccolith formation. This is a coccolithophore cell. It started naked without any coverage. And then you can see that it is forming the mineral inside. And only once it is ready, very suddenly, it is exocytosed to the surface of the cell. And immediately, the process starts again, and another coccolith is starting to form inside of the cell. So if we are interested in understanding how the crystals are forming and what is controlling them, we need to study a process that is happening inside the biological environment of the cell. There is actually an organelle in which the crystals are forming. And this proved to be very difficult for many times because to study the chemistry, the material science, the crystal growth phenomenon inside the cell is difficult. It is incompatible with many of the biological tools that we used to have. And for a lot of time, this was a big challenge that, so what people did is to study extracellular coccoliths to understand how they are made of, use the available biological techniques, and this was very informative for many aspects. And here I'm summarizing in 3 points what we know about the coccolith. So a coccolith is basically an array of calcite crystals. The calcite is the inorganic building block. But actually, what is important for the formation and the control is the organic fraction of the coccolith. And here there are 2 different kinds of organic molecules that is worth to mention. One of them is a soluble macromolecules, mostly negatively charged polysaccharides, that are enveloping each and every one of the crystals. Very thin coverage that is delimiting every crystal from the other. And the other component is an insoluble fragment. It's a scale, we call it a base plate, which is underlying the entire ellipse of the coccolith. It is made mostly, it is made of cellulose fibers. I hope that you can see them on your screen, that are giving this elliptical scale its shape, its morphology, and the crystals are going on the periphery of this scale. So after knowing this basic concept, people came up with a mechanism, what they were proposing to be the sequence that is leading to the controlled formation of the crystals. And basically what this model is saying is that the base plate is a template, a stereochemical template that has some structural features or chemical features that giving rise to the oriented nucleation of the crystals. and that after the crystals started to grow, then in order to diverse them to the right morphology, we have interactions with specific soluble modifiers that are interacting with one crystallographic plane or the other in order to give rise to these different morphologies. And this is a model that was hypothesized more than 30 years ago, and according to this, this is what we thought about the formation of Coccolith. And what I want to highlight is that the conceptual framework of such a model is rooted in the chemistry of solution-mediated crystal growth. Because we think about it similarly to what we think about crystals that are going to grow in a beaker. We are thinking about aspects like supersaturation, like epitaxy between the template and the crystals, stereochemical interactions between modifiers and the crystals. Those are many things that we know that are working and that are happening in solution, in crystal growth from solution. And if there is one take-home message that I hope that I will convince you that you will take from this talk, is that the very important factor that is different is that the formation of these biological crystals is happening inside a very confined organelle. The solution there is very limited. It is bound by organelles, by the membranes of the organelle, and this is making many of these processes different, even irrelevant at a certain aspect. So we need to think differently when we are thinking about intracellular crystallization of these crystals. So how do we, yeah, this is just an animation. So how can we study this formation inside the cell? Luckily, the technology is improving very fast, and today we can do many things that were impossible 3 decades ago. And the one important tool that we are using is cryo electron tomography and electron microscopy, because today the microscopes are so good, the detectors, the preparation facilities, so we can get structural information from in vivo-like conditions, and also get some characterization of the chemistry of what is happening inside the cell. And I will tell you what is the scheme, how we are preparing for such an electron tomography experiment. So we are culturing our cells in a growth room. We work on model species that we know exactly how to culture them and to synchronize the state at which they are producing more and more of this Coccolith. Once we know that this is the right point, so they are producing Coccolith, we take just few microliters of the solution, we put it on the microscope grid, and we vitrify. Vitrification means that we are freezing the cells so fast that even the water molecules don't have the time to rearrange into ice crystals. So everything is locked in its native state, and from now on, all the measurements are done at cryo conditions. So we are really looking on the conditions as they were when the cells was alive and mineralizing. Now, these cells are too thick for the transmission electron microscope, so we need to thin them. We are using a focused ion beam that is removing a lot of the material above and below the middle of the cell. So what we really are left with is a very thin lamella. It's about 200 nanometers in thickness. And this we can take into the TEM and look on the cell, what we have inside the cell, choose the regions of interest, and then collect the tomography data. Tomography is the same thing like doing a CT scan. We are taking many images at different tilt angles, and from this we can reconstruct the three-dimensional information of what we had inside this tiny volume, about 200 nanometer in thickness, half a micron in the X and Y. And then we can label. We can label the membranes. These are the layers that you see here, the crystals in blue. We can see other scaffolds, and we can ask questions and learn about what we saw inside of the cell. So I will tell you what did we learn about this intracellular process of Coccolith formation. This is in general what we knew, what we were expecting. It's a process that is happening inside an organelle. We call it the Coccolith vesicle. This organelle is membrane bound, and the process is sequential.
first we have the formation of this base plate, the organic scale. Then there are some particles that are loaded with calcium that are joining, fusing, and the crystals are starting to grow on the periphery of this base scale until it's mature. And this is how it looks in the microscope. This is a timeline that I'm just showing 5 spots in this timeline that are showing how this process looks like. Each one, you are just looking on the edge of the Coccolith vesicle. So these are the membranes that are delimiting the vesicle. In purple are this organic base plate. It has different layers. We can see the fibers that are making it. We can see the crystals. Here, this is the tiny crystal that is just nucleating. They grow, they are getting their shape. And we can also see some other stuff inside the vesicle, like this very dense red balls that are this calcium precursor that are bringing calcium into the vesicle. And there are many lessons that we learned from such type of data, and I will try to break it to 4 points that I want to convey here. And the first point is focusing on the initial stages when the crystals are nucleating, because this is the tiniest, the smallest crystal that we saw, but this is like a time point before. It's not the same cell, of course, but we saw occasionally that we have very dense globules that contain a lot of electron-dense material, supposedly calcium, and then they turn out into these crystals. And the notion was that the base plate is the one that is interacting with soluble calcium and carbonate molecules in order to template the formation of the crystal. But actually, when we look about different base plates from different species that give rise to very different coccoliths, the base plate is having a very similar basic architecture, ellipse with radial and concentric fibers. Sometimes it is wider or more deteriorated, but it's the same thing. We couldn't really see any structural aspects that can be responsible for the templation or the templating the crystal. What we can see is the surface reaction, because both in vivo and also previously in vitro, we saw that on the periphery of the base plate, calcium is forming a very dense phase that we call a coacervate. Coacervate is electrostatically forming precipitate on a specific location. And the formation of this coacervate or a precipitate can be tailored such that at specific concentrations, it is happening only on the right places, on the base plate. So before the formation of the crystal itself, there is another phase that is dense, rich in calcium, that is templating, locating, guiding the crystallization to the right places. And this notion of a dense phase, which is not just the soluble molecules in solution, is something that is very important for cell biology. Because even when looking on the broader perspective of the entire cell, we could see that inside the cell there are many different kinds of dense phases. This is an X-ray microscopy analysis in which dark contrast in this map means more calcium. So there is more calcium in the coccolith outside, but also on the coccolith inside. But there is another completely different organelle, a vacuole, that is containing calcium-rich deposits. And these are not direct precursors for the coccolith because they are not in the same way, but the cell is loaded with calcium. And I think that the better way to think about the biomineralization, cellular crystallization in general, is to think about these soluble ions that are there in seawater getting into the cell and then being incorporated into one dense phase and then to another and to another. And the role of solution in the cell is really minor relative to what the role of these dense phases. And here is an example for how this can be important for how we think about biomineralization. Because we are, for the last decade, concerned about ocean acidification and how ocean acidification will affect calcifying organisms, and coccolithophores are one good example for that. So in one of the worst case scenarios, by the end of this century, the pH of the ocean will decrease about half a pH unit from about 8.2 to 7.7 or 7.8.
This is the effect of all the anthropogenic CO2 that we are putting into the atmosphere. But when you take such a pH change and you make the calculation how this will affect the concentration of proton in such a small volume, and this is the volume that is the aqueous lumen inside the organelle, the lumen that is not taken by dense phases and crystals, you get the answer that is only about 1 or 2 protons that will cause this ocean acidification if they are getting into the vesicle or getting out. And this is obviously of no physical importance. I don't think that 1 proton in or out will change something about the overall formation of these huge crystals that are going inside the organelle. So my point in this calculation is to deliver the message that when we are thinking about confined volume with dense spaces, a lot of macromolecules that are binding a lot of atoms, maybe the nominal pH value is not really the driving force for controlling the kinetics or the thermodynamics of the process. We need to think about other things like fluxes, ions getting in and ions getting out, and a combination of these ions into different phases. And the last point that I want to make from this kind of data set is about the process of crystal growth, because maybe the most obvious feature of the Coccolith is the morphologies of the crystals. And when we were looking on the crystals, we saw several observations. One of them is that the membranes of the Coccolith vesicle are very tight around the crystals. So in a way, they are molding some aspects of the shape of the Coccolith. And molding by membranes is something that in biomineralization is associated with the precursor phase. And we know that there are many other ways to form crystals that are not just by the addition of ions to the crystals. We can form amorphous precursors, droplets, or crystalline. But in this case, what I think is happening is actually a very simple ion by ion growth process, because these particles that are bringing the calcium ions complexed with the negatively charged polysaccharides are actually dissolving as they are getting closer and closer to the crystal. So we did here an analysis, and we saw that for growing crystals, the size of this precursor is diminishing as a function of how close they are to the crystal. So we think that at least part of crystal growth that is happening on these crystals is very similar to an ion by ion growth, which is also can explain why we see sometimes crystallographic facets in the morphology of this crystal. And this will bring me to a specific story that I want to tell you. This is the project of a PhD student, Emmanuel Avrahami, in which we try to understand more mechanistically how the morphogenesis of the Coccolith crystal is controlled in the cell. And for this specific project, we were focusing on a model species, which is called Calcidiscus leptoporus, because it is producing these very relatively large crystals that have a very distinct morphology. They also have 2 shields, and they have this arrangement of alternate crystal units. The R units in blue, they are coming from the fact that the C-axis of this unit is radial, and V for the orange ones, because these units have their C-axis vertical to the plane of the Coccolith. And we wanted to understand how this morphology is being made inside of the cell. So Emmanuel set up a procedure in order to isolate intracellular Coccoliths that are during the formation stages. So we are starting with a culture, and this culture we treat such that many of the cells are at different stages of forming new Coccoliths inside of the cell. Then we are dissolving all the external Coccoliths because we are not interested in fully formed Coccoliths. So we have naked cells only with intracellular Coccoliths. Then we are rupturing the cells with conditions that still preserve these intracellular Coccoliths that are now released into the environment. And then we can collect them and do the microscopy investigations on intracellular Coccoliths that were extracted and preserved in their formation stages. And using a preliminary SEM analysis, we could see that this is the qualitative timeline of the formation of the Coccolith. This is from above, the distal view, and this is from below, the proximal view. And we can see very nicely the morphology of the different units, crystals, and how it is growing and progressing. But we wanted to have a quantitative view, so in order to do that, we collected 3D information using electron tomography. Because with electron tomography, we can get a nanometer scale resolution, we can have a 3D information, so we have a very good representation of the shape of the crystals. We can segment the blue unit from the orange unit and see how each one of them is looking in 3D. So what Emmanuel did is to do it for several data sets and to reconstruct a timeline of how the morphological evolution of the different units looks like. And you can see it's starting from something very simple, looks like almost a normal rhombohedron of calcite, and then it's developing into the more convoluted shape. And in this more convoluted shape, some places that look curved are really the manifestation of the molding by the membranes of the vesicles that are supposedly putting a barrier here, and the crystals are going to different sides. But in this morphology, there are also very flat faces that look the same like a crystallographic habit of a crystal. So we started to focus on these crystallographic surfaces. And by looking at them from different angles and measuring the angles of the surface, we can assign the crystallography to what we saw. And in this case, it's not very difficult because this really looks like a calcite rhombohedron. Here we are looking down the z-axis, so we have this roughly threefold symmetry, and these are the three identical sets of the 104 facets. What we thought is that when we will look on the more mature crystals, we will see more things, more facets, something that will explain how different coccoliths can get different shapes, different morphologies. And here it was the big surprise for us, because when we looked on these mature crystals, the only crystallographic facets that we could see are the same rhombohedral facets of calcite. So this is something important that it took us a while to believe it. All the crystallographic facets that we see are the rhombic facets of calcite that we will see in the most common calcite crystals. But these crystals are very different from this rhombohedron. They go anisotropically. So what we should conclude from that is that we only see the stable crystallographic planes of calcite, which are expressed in this morphology, but these symmetry-related facets are growing anisotropically. This purple facet is growing much faster than the yellow one. This is why this crystal is becoming very elongated. And I guess for some of you it is bothering, because to say these two sentences together is unheard of. This is something that is contradictory to very basic knowledge about crystal growth, and I will explain what do I mean. Because we know how a crystal should grow. This is the young crystal, and all of these black facets are identical. This crystal should grow isotropically. And this is something that we know that is happening. Now, okay, we know also how to grow crystals anisotropically. Usually what we are doing is that we are starting with this young crystal and we are putting some additive, something that will interact with specific other facets in order to slow them, and then we can get an anisotropic morphology of this crystal. But what we saw in our data set is this thing. We saw identical facets that are growing at different speeds. And this is impossible because they are chemically identical. There isn't any physical entity in the world that can differentiate between this facet and the other one. So what is the solution for this? How this is what is happening inside the cell? And at the end, we realized that this is really impossible inside a homogeneous environment, what we are usually thinking of, a beaker, something that diffusion is mixing and homogenizing everything that is happening around the crystal. But this is not the environment inside the organelle, the Coccolith vesicle. This is a very confined environment in which we can think about heterogeneous environment. Because if this is the membrane of the Coccolith vesicle, and through this membrane there is some transport of, let's say, bicarbonate ions inside, if this is the location, the hotspot of transport, here there will be a higher concentration. On a different place, there will be a lower concentration. So the crystal is not seeing or sensing the same environment from all of its sides, and this is what can make the anisotropic growth occurring. And we were looking back to the data to see if we can see some verification for this hypothesis, and there are several cases that look exactly like that. So here is one example. This is the most straightforward one. We start with an isotropic crystal, but because this apparent flux of ions is coming from one side, from this side, then this crystal is going preferentially toward the source of this ion. But more interestingly, this heterogeneous environment can explain more subtle details about the morphology of the crystals. So here is another occasion when the crystals are premature, quite young. What we see here are 4 different crystal facets that are very close to each other. They are parallel, they are facing the same environment. So here we cannot really invoke the thing of heterogeneity because these are tens of nanometers away. And yet, when they grow, all of the time, these orange faces are growing faster and they cover the blue faces. So how is it possible that this phase will go faster from that phase? And this is possible because these are the same faces, but with opposite orientation. And if the orientation is opposite, so the orange phase is showing the obtuse angle to the high concentration side, and the blue one is showing the acute step to the high concentration side, this is what is causing the differentiation in growth kinetics and making the orange one grow faster. So the heterogeneity here is affecting differently one orientation from the other and is causing this decoupling of crystal growth from the same identical crystal. And the last thing that we learn from this data set is that if we are looking just on the basic rhombohedral morphology of calcite, it can also explain another very interesting trait of Coccolith, which are the chirality, because Coccolith structure is chiral. You can even see it here in this young Coccolith. And chirality was assumed to be the result of chiral growth, something that will modify the growth into a chiral stage. But what we see is that the initial arrangement of the crystal is chiral, and this is because the simple rhombs are located with one of their edges on the base plate. So the original mechanism or model assumed that the c-axis is exactly vertical or radial, so the crystals don't have any radial orientation. But what we see now in our data is that actually each one of the crystals is located on their edges. It is forcing some tilt that we see in the orientation of the c-axis, so it is not really vertical or radial. And on top of that, it is inducing a chirality to the structure that is maintained as the crystals are growing. Now, we don't know how this chirality is controlled or maintained, and it is also very interesting that you can have both chirality just if you choose to put the crystals on this side or the other one, and still in biology, it's only one type of chirality that we observed, that we can observe in the Coccolith. Okay, so this brings me to my summary, and I hope that at least these 3 points I managed to convey. First is that these new tools of electron microscopy and tomography, they really allow us to go deeper into the process of biomineralization and understand the in situ, in vivo processes at a 3D nanometer scale inside the biological sample. When we look at this, we realize that the nano environment is a very important factor that is guiding crystal growth. And it means that certain things that are very pivotal in bulk solution will not be so important on this nano confinement, and vice versa. This nano environment can really force the crystals to grow, and this can be a reason why we can see an anisotropic growth. That is the most important thing that shapes the Coccolith crystals into their different morphologies and species-specific morphologies. With this, I'm done. Again, I want to acknowledge my group. This is a lovely spring day about 2 years ago. If anyone is interested, we are always looking for more people. Our collaborators, especially Yulia Mahamid, that taught us all the things that we know about electron tomography, and you see how important it was. Funding, and that's it. I would be very happy to answer some questions.
Yeah, so thank you very much, Assaf. If there are any question, you can either ask them with your voice, or you can type them in the chat and I will read them. So is there anyone who has a question currently? So yeah, Karim, if you want.
Yeah, thank you, Assaf. It was really wonderful, impressive. The quality of the images and everything you can get about the growth and the architecture of the Coccolith. That was great. So I guess I would have many questions, but I try to keep up with only a few of them. Just so maybe quite specific questions about those particles that are electron dense and that you see are most likely loaded with calcium and that might be precursors. Eventually, do you have any idea about what they are?
We think that they are quaternions, so that the precipitation of calcium with the negatively charged polymer, those are usually polysaccharide, polyuronic acid. We can repeat it in vitro, so we see a very similar thing when we are mixing just calcium with polysaccharides that we extracted. I don't know what is controlling the dissolution or precipitation, those specific chemistry. This is something that I don't know, why they are so dense at one location in this organelle and less than on another location.
Okay, and another question is so about this homeostasis of calcium. I mean, what you show is that you get calcium might be in polyphosphate, or I think you call that calcium phosphorus rich stuff bodies. I was wondering, do you have any clue about what's going on here? Is there some connection with day and night cycles?
Yeah, this is something very recent that we are just making sure that we understand it. So in general, I think that this calcium store, which is in the form of calcium polyphosphate bodies, is not unique to calcification. We see it, as you know, in many different calcifying and non-calcifying organisms. And in the case of the coccolithophores, it might be related to the calcification directly, but more probably, I think, indirectly. And now what we see is also that their formation is more related to the energy state of the cell, not to calcification. So when they are in the dark, they need to respire, they consume this calcium polyphosphate, and when they are photosynthesizing, they produce them. So I guess from your question that you also see something similar. So it's
yeah, completely. We see but we think there might be, as your number 2 arrow. I mean, there might be some connection between two or a re-exchange, and we see a day and night shift between the calcium going to the polyphosphate or the carbonate. So it's really nice to see that. Okay, so
just the formation of this dense calcium polyphosphate granules is interesting, because this is also, it's like a one cell with two biomineralization phenomena, except of one, and they are not directly related, so both of them are equally interesting.
Yeah. Okay, thank you.
So I think Nia has a question after that. Adrien has one as well. So Nia, if you want to ask it. Nia. So yeah, we can't hear you, Nia. I don't know if. Well, never mind. In the meantime, I can read Adrian's question. So Adrian was asking, what advice or tips would you give for people wanting to start cryo studies on biomineralization?
Go do it. Let me see. One very important challenge is the size of the sample. So we are working on these unicellular organisms because it's so much easier to vitrify cells that are less than 10 microns, even better, less than 5 microns. So this is so much easier to do on bacteria or protists and not on bigger things. And the other one is that it is very helpful if you can synchronize something about the precipitation, because still electron microscopy, cryo microscopy is a very low throughput technique. So we need to know that the cells that we are preparing, 80% of them are going to be interesting. It's not a method to scan through many cells that are just not calcifying now. But do it. It's a very powerful technique.
Okay, so Moniz has a question as well. Do you want to take Moniz so I can read it? Okay, so I'm going to read it. So Moniz wrote, thank you for the talk. You spoke about the difference in microenvironments in the vesicle and outside. Do we know something about this heterogeneity in terms of different ion concentration, etc.? So yeah.
Yeah, it's a very good question, because it is very difficult. We practically don't know any specific quantitative value of how much, let's say, calcium we have inside the vesicle or carbonate or something like this. And this is something that we are trying to see if we can do with some kind of electron microscopy, because we want to really measure quantities inside volumes that are tens of nanometers. What I think is maybe more probable in the near future is to have a relative amount, because we know that we have calcite, we know what is the concentration of calcium in calcite, we have the cytoplasm, we know, so we can estimate like ranges of concentrations, hopefully, in order to get a more quantitative view.
Does anyone have another question? Yeah, so Karim has another question.
Yeah, I have another one. I don't know how related it is, but I was wondering about the fluxes within the cells. I mean, do we know? So you have the precipitation of calcium carbonate that will consume protons somehow, and I was wondering how it compares with the the other fluxes of protons within the cells. I mean, for example, does the calcium carbonate precipitation somehow balance the photosynthesis, or in Coccolith? I don't know if we know.
Yeah, it's really interesting. There was a recent study by Colin Brownlee and Glenn Wheeler's group that they are able to measure proton fluxes from the plasma membrane with clamp patch, and they see that cells that calcify, they need to alleviate the proton load, because actually they are taking bicarbonate and the calcification is producing protons that they need to take out. What I think, and I don't have any proof for that, is that also on the membrane of the Coccolith vesicle, you need to have such proton channels or pumps, and I think that maybe they are the really important ones in order to direct the growth of the crystals, because I think that calcium is being loaded through the ER. So it's very general. Calcium is not limiting inside of the vesicle. Possibly also the bicarbonate in is not just a big problem because you have a lot of bicarbonate in the cytosol, but to take the proton out, this is what can trigger the further growth. Right now, we still don't have a handle how really to localize specific machineries like proton channels or pumps to find it. So I don't know, but I think it's really interesting.
Yeah, I don't know if Nia has fixed audio issue. Nia? No. But I do have a small question. You might have said it in your talk, but the organelles, the membrane of the organelles, what are they made of?
The membrane themselves are very usual lipid bilayers. We can even see with the tomography data. I don't think I have it here, but we can identify membrane machines like general ATPases. We don't have enough resolution to say which they are, but it is just a membrane like any other organelle in the rock. This one is really manipulating ion fluxes in a very unique way.
Okay. And do they have a specific forms, or because I mean, if you say that the shape of the organelles can shape the crystals, do these organelles have an already defined shape before the crystals start to grow, or not really?
Not really. It's starting like a very plain vesicle. And we used to think that in order to shape the crystal, you need to have something like a cytoskeleton to stop, to restrict the further growth. Right now, I'm not sure that this is the direction. I think that maybe something like the localization of proton channels at specific places will make the crystal grow towards a specific direction rather than to stop it from going to another one. It will go where it can go, and therefore the shape of the membrane is like something that is with instantaneous feedback with the growth of the crystal. So I think the two of them are related.
Okay. Yeah, thank you very much.
And Assaf, about that, so that was your model eventually, finally, so about the preferential growth around some direction, so that basically your preferred idea is that you tend to favor growth against along some direction instead of inhibit the growth along other directions?
Yeah, it's actually, I think it's a combination, but inhibiting is not active inhibiting by the binding or something or the physical force. I think inhibiting is depriving from further growth. So if you put a membrane that is not transporting anything, the crystal will not grow. And if you put channels on another place, then it will grow. What we know for sure from this data is that there isn't any role for stereochemical additives in shaping the crystal morphology because the only facets that we see are the rhombohedral facets. They are identical. We don't know if there are other functions of these soluble molecules that are in there.
But could you imagine some inhibiting molecules that would be on specific area or portions of the membranes, and and then you would have something anisotropic?
Yes, but like you said, it will need to be on the membrane because the crystals, it cannot, it's identical. The membrane, this is where the morphogenesis, I think, is more coming from. So it's like it's shifting, at least my thinking, from stereochemistry of crystal growth to a lipid raft of cell biology.
Okay, do we have more questions? Okay. So maybe Nia, because she's struggling to connect.
If anyone really wants to continue, I will be happy to send me an email, and I'm looking forward to have more exchange of ideas.
Yeah. Well, if there is no more question, I think we can finish this seminar.
Sorry, I have just one question about the strontium. I was wondering, did you try to enrich your media, whatever, to have a higher concentration of strontium and see what's happening about I mean, even a selectivity or something where is going on, the excess or what's his consequences of the cell morphology or whatever?
It was done not by us. So if you put too much strontium, then you cause some not specific stress to the cells. So also the Coccolith start to look bad, but it's not very specific kind of stress. We don't know exactly what it is doing. They are tolerable to something. I think that an order of magnitude increase in strontium concentration is still okay for them. And this will also cause an order of magnitude increase in the strontium fraction inside the crystal. The calcite is very clean. They don't really incorporate a lot of additives, but strontium is relatively more something that they will take. So we use this as a proxy to try to follow the strontium, but they don't take much. So we were limited by the amount of signal that we can get from the strontium.